Memorizing the names and formulas associated with each law is not as important as grasping the underlying principles. What truly matters is understanding the fundamental concepts and how these laws relate to each other. Recognizing the broader patterns and connections allows us to derive these laws from more comprehensive equations and theories. This approach not only simplifies learning but also empowers us to comprehend the interplay of various factors in chemical phenomena. For example, we can derive Boyle's law by using the equation of state. Upon identifying that the exercise explicitly states that the temperature is constant, we must also assume that the amount of substance is constant. Then, assuming the maxim axiom, that any operation between constants results in a new constant, we obtain the static form of Boyle's law. Now we just need to solve for one of the variables, for example, the volume in terms of pressure. We obtain an inverse similar to 1 over x, whose graph is the inverse of a line. Boyle's law is the only one that results in an inverse of a line. Deriving the other laws, therefore, becomes a matter of finding the explicit constant, assuming constant quantity of substance, and simplifying using operations among constants. For instance, if volume is constant, we combine the implicit and explicit constants and obtain gay-Lussac's law. A linear and increasing relationship between pressure and temperature. If we assume that pressure is constant, merge it with the other constants, and obtain Charles's law. Remember that in these three laws, we implicitly assume that the quantity of substance is constant, which is equivalent to assuming no leakage or entry of gas. Avogadro's law is interesting because in this case, the quantity of substance does vary, while the constants are pressure and temperature. Another uniqueness is that the constant generated is historically significant, known as molar volume. Its standardized value at normal conditions of 0 degrees Celsius and 1 atmosphere is 22.41 liters per mole of substance. The mass of many gases measured under these conditions forms the foundation for constructing the original table of atomic weights. As a result, we can assert that the original definition of the mole was the mass contained in 22.41 liters of gas under normal conditions. This definition later became associated with particles as Avogadro originally envisioned, but this transition was achieved by Albert Einstein and Jean Perrin at the beginning of the 20th century. Well, that's all for now. I hope you've enjoyed it. And I'll see you next time where we'll learn how to convert these static or state definitions into the formulas we actually use to solve pencil and paper exercises.